I think today's event is really a testament of what the public university is all about, because our speaker was educated here at UCI, got her degree in 1998, and then went on to do her PhD at Caltech. I'm proud to say with a former PhD student of mine, also a UCI product, and then went on and did some postdoctoral work at Berkeley. V is really a phenomenon, I think would be fair to say. She started her academic career in 2006 at Toronto, and University of Toronto, I think, is widely regarded as probably the top university in Canada, a truly wonderful university. Within 4 years, she was promoted to tenure, and 2 years later, I'm sure they were thinking about promoting her to full professor, but we luckily got in the game and were able to bring V back. She arrived on the campus in this summer, in July, and very rapidly has built a very vibrant research group. I'll just point out that we have maybe 20 or 25 entering organic PhD students. She's an organic chemist, and I think about half of them wanted to work for V, which I would say is really a testament to their good taste. Well, V works in the area of synthetic organic chemistry, and that's the area that is all around you. You know, the car you came in this morning has a number of parts that were made by synthesis in organic chemistry. The food we're eating, some of it's helping its production came that way. I think those people like me that have the white hair, the Lipitor we took this morning is a product of synthetic organic chemistry. And V is one of the world leaders in the synthesis of new molecules using catalysis. And that's what you'll hear about today. And I won't say much more about her, but just to point out that just in the last 5 years, V's given more than 100 invited talks. She's spoken at most every important conference for organic chemistry in the United States and around the world. I think she hasn't been to Australia, or have you? I think that's the one continent she hasn't been in. But besides her, the real mark that she's made on scholarship, she's a fantastic educator. There's a table back here, I think, of some of her current students. I've met her students for several years, and they're always, they couldn't have enough nice things to say about the type of mentoring and teaching she does. I think that also translates into her lecturing in undergraduate courses. So I know you didn't come here to see me, so let me introduce Professor V. Dong.
So good morning, everyone. Thanks very much to Larry Oberman for that very kind introduction. I'm actually glad we have this on tape so I can show my parents later how amazing it was. So it's really a great honor to be here, and I wouldn't be here if it wasn't for the amazing education that I did receive at UCI, and taking Larry's class really changed the course of my life. I changed my major to chemistry. I had the chance to work in his lab and do research for the first time, and then I even met a guy in his class that I ended up marrying. So Larry likes to take credit for that as well. So what I'd like to share with you today is a bit about our research program, and as the Dean mentioned, we moved from the University of Toronto recently, so thought I'd share with you our journey over the summer. So we started out in Toronto, and my graduate students got gigantic reams of bubble wrap, and they wrapped all of our equipment up, and then we stuffed everything into a 26-foot truck. We filled it to the brim, basically, and we finished this about at 3 a.m. on a Sunday morning. And then my husband, Wilmer, drove the truck for 3.5 days, pretty much straight from Toronto to Irvine. And we unpacked in about a week and started doing chemistry. So we're at Natural Sciences 1, a really beautiful space. It's about a 10-year-old building. And my students have done a great job of setting this up. And so one good result of this, as Larry mentioned, I've been traveling a bit over the last few years, and after this trip across country, I went to China to give a lecture. And after a 14-hour flight, I got off the plane and thought, well, that wasn't really bad at all. After being in a truck for 44 hours, it really kind of changes our perspective, or my perspective on traveling. So it's really great to be here. It's been a fantastic time at UCI. And I'm honored to have this chance to meet many of the members of the community here and give this lecture today. And so this will be a very different lecture than ones that I typically give. I wanted to start off with introducing who we are. So a large number of new students have just joined my lab, and a couple of weeks ago, my husband and I had everyone come over to our house for what I call the State of the Union, or State of the Group address. And so during this time, we discussed with the group what is our group's mission statement. And one of my students, Dan Kim, actually did a really nice job of reciting the mission statement to me from memory. And so this mission statement really has two parts to it. As a research group, we want to train synthetic organic chemists to go on to be leaders in both the pharmaceutical industry and in academics. And so I hope to convey to you this one idea of what kind of training does a synthetic organic student receive, and why is that important to our society. And in addition to this, another part of our mission statement is this idea of contributing to society through innovations in organic synthesis. And so another goal for today's lecture is to convey this idea of why is organic chemistry important, and what kind of contributions are my students making in this area. So as a teacher here, one thing I've realized, a good way to capture the attention of your audience is to let you all know that all of this material will be on the exam. So to start off with, this is my group of students, and I do want to start acknowledging them. Do you guys want to raise your hand? They're sitting at these two tables in the middle here. So these are really the faces of the people who are doing the science. And sometimes we have this conception of scientists as being people who look like Einstein. And really they're a young group of people in their 20s and 30s, dedicating their life, working in the laboratory to do this. This is a bit of an exaggeration. This little guy here is Ihan's son, so we're not training him that early. But when I think about my students, looking at some of the things that they do, Diane here has this shirt that really does describe her life right now. It's eat, sleep, and chemistry. And if you look closely at the shirt, actually, the eating and the sleeping also involve chemistry. So, Diane's eating sugar, she's sleeping and producing this amino acid that helps her relax. The chemistry here is actually an explosive, and this is actually something we try to avoid doing in an organic chemistry lab. So, in addition to this, my students typically are students who have gotten into the field of organic chemistry because they love building things. And so oftentimes they've told me, as children, they love playing with Legos. And in fact, Colin hasn't grown out of this. He has a jar of Legos still on his desk in the laboratory today that he likes to tinker with. And so these students are really passionate about organic chemistry. They love building things. And so, the building blocks that we use, though, as synthetic organic chemists aren't Legos. Rather, they're the elements of this periodic table. And the main building blocks that we use are carbon, hydrogen, nitrogen, and oxygen. So these pretty much make up all of these structures that I will talk about today. These are the fundamental building blocks. When we snap them together, that's a chemical bond. And so what I'd like to share with you today is the way my students think about designing new organic structures using these main elements. Okay, so this is another question I'd like to introduce. What is organic chemistry? So the blondes here are dentists, and when I go to my dentist and I tell them I'm an organic chemist, they're usually not too happy with me because sometimes organic chemistry is thought of that class that prevented me from doing well in college. So I hope you guys don't feel that way. But what is organic chemistry? So if we think about this topic and kind of boil it down, organic chemistry is basically what Larry alluded to. It's basically the study of almost everything, basically everything containing the element carbon. So carbon is really the most important building block in this story. It's the key building block for everything organic. And so when we look at this fuzzy creature, the anteater, right, the basic building block here is an amino acid made out of carbon, hydrogen, and oxygen. So this is the basic building block of life. And we'll talk a little bit about my group's interest in these amino acids. When we think about DNA, which we often think about as an essential molecule because it encodes our genetic makeup, if we look closer at this molecule, it's also made out of carbon, hydrogen, nitrogen, and oxygen. Right? These 4 nucleotide bases that are so important for passing on our genetic information. When we look at what we're eating this morning or later this afternoon, right, these molecules that give us energy, again, made out of carbon as the main building block. And also our medicines, new discoveries, molecules that don't even exist yet. This is an example of Gleevec, which is considered a miracle breakthrough cancer drug for treating a rare form of leukemia. And when we see this structure, again, it's an organic molecule made out of carbon. So synthetic chemists, we like to use this cartoon to depict these organic molecules. And you'll see this over and over in my lecture. Every point here on this chain is a carbon atom. So this is carbon, carbon, carbon. And then we'll see the other elements highlighted, just drawn in. And so these are the cartoons that make up these organic structures. So what this slide tells us is basically almost everything is organic chemistry. So my students are interested in studying the properties of the structure, their conformations, their reactivities, and especially thinking about how do we make new organic molecules. So I'd like to use this analogy. I think it's a useful one. It's not perfect. This is a photo from Hal Moore, one of my chemistry professors, the early days of UC Irvine. I know we have a lot of alumni in the audience here. When I was an undergraduate student here, we used to say that UCI stood for under construction indefinitely. There was always something being built. And looking at this early photo of what the campus looked like, just a few decades ago is kind of amazing. An analogy that we like to use is that an organic structure is like a building. It has a specific shape, it has a 3-dimensional structure. And so when we think about building a building like physical sciences or natural sciences, there are many people involved in planning this building and designing it. And so we have our architects that provide the blueprints. We also have to have the tools like the hammers, the bulldozers, the basic tools that allow this building to be constructed. And then we have the construction workers who actually put the building blocks together and construct this 3-dimensional structure. So what do my students do? Well, the students that are trained in organic chemistry actually have to do all of these things. They have to be the molecular architect that designs how to construct the molecule. They have to actually sometimes invent new tools. Sometimes there's not ways possible for us to build these molecules, and so we invent catalysts that allow us to hammer together these 2 atoms. In addition to this, the students are also the construction workers. They go into the lab and they actually run the experiments and make these new bonds. Now, I said this analogy is not perfect because unlike a building, my students have a really challenging time seeing the molecules. They're not something that we can analyze by just looking at them. And so they also have to be trained in indirect techniques like spectroscopy to try to figure out what they have actually made in solution. And sometimes it's not what we expect. Okay, so the training aspects is that the student basically has to be a designer, a synthetic chemist, and also a detective in trying to figure out what they've made at the end of the day. So another sort of property of molecules that I'd like to discuss today, and this is really critical for our research program, is this property of molecules called chirality. Chirality is a word that's based on a Greek word meaning handiness. And so if we look at our 2 hands, they're mirror images of each other, but yet they're not superimposable. Right? We've got the left hand and the right hand. So in 3-dimensional space, our left hand and right hand, even though the connectivity looks the same, right? My thumb is still next to my pointing finger, which is next to my middle finger. These are distinct 3-dimensional objects. So it turns out that molecules are also like our hands, in that you can have a left-handed molecule and a right-handed molecule. 2 molecules can actually exist as mirror images of one another. So how is this possible? So to better understand this concept, I want you to imagine a tetrahedral structure. And this is the basic shape that a carbon atom has when it's connected to 4 different things. So if we take carbon here in the middle and attach it to 3 hydrogen atoms and 1 generic atom X, you can have a mirror image, but these two mirror images are actually superimposable. So you can put them on top of each other, they're the same molecule. Now if we go down to this diagram, where carbon's attached to two hydrogens and two different elements, again, its mirror image is actually the same as itself. There's a way to rotate it and put this on top of itself. And so we have some models that we can play with to understand this concept. But at this bottom structure here, if we look at this carbon atom, it's tetrahedral with 4 different things attached. Now the mirror image is completely distinct. Right? It's like a left hand and a right hand. These are non-superimposable. And so these two molecules are what organic chemists call enantiomers. So I often say organic chemistry is like a foreign language. There's a lot of new words that we have to learn. So for today's class, we're only going to learn one new word, and that is enantiomers, right? Molecules that are mirror images of each other. So why are enantiomers important? Well, if we think about it, our biological systems are also made of molecules that are chiral, that exist as one specific mirror image. And so it turns out that the chirality of a molecule dramatically impacts its biological activity. This is an example of how amazing our nose is at detecting enantiomers. So these two structures are exactly identical in terms of their chemical composition. They're made out of the same carbon, hydrogen, nitrogen, oxygen. They have the exact same molecular formula. But in three-dimensional space, we can see that in this case, this molecule is the right-handed one, this is the left-handed one. They're actually mirror images of one another. So another way we depict these molecules in terms of drawings is that this wedge shows that that bond is pointing out towards us, and the dashed line shows that the bond is pointing back behind the screen. So one enantiomer of this molecule is caraway, while the other one is spearmint. And so we can actually detect this. Our nose is sensitive at identifying the difference between these two enantiomers. So the idea of making enantiomers selectively and the importance of enantiomers unfortunately drew a lot of attention in the public due to one of the greatest medical tragedies of our times. So in the 1950s and 60s, there was a drug called thalidomide that was approved in Asia and Europe. And the story is much more complicated now, and we know much more about how this works. But at the time, it just became discovered that the right-handed enantiomer of this molecule was useful and could be effective in treating morning sickness for pregnant women, whereas the left-handed, the mirror image of this molecule, was what was actually causing birth defects in babies. And so there were a generation of children, about 20,000 children that were born with this birth defect. Their limbs were not fully developed. And so as I said, the story is a bit more complex because these two enantiomers actually can interconvert. But this made it really important to chemists to think about this idea. When we build these molecules, how do we make one enantiomer in preference to the other? Because we know that the chirality of these molecules are very important for their biological activity. So that's the challenge that synthetic chemists are posed with. How do we construct these three-dimensional structures in space and control the mirror image that we produce? Okay, so this is a question for you guys, for everyone to think about this morning. How can we make one mirror image of a molecule? So to think about this, I do want to introduce a little bit about chemical theory. The way that synthetic chemists think about making and breaking bonds is based on transition state theory. And the analogy we have is that when two molecules come together and collide, they have to come together at the right geometry. They have to also have the proper kinetic energy. And we think about an energy barrier. The two molecules have to have enough energy to overcome this barrier in order for a new bond to form and an old one to break. So sort of like these rolling ski hills. Okay, these energy barriers, if they're too high, the transformation is just not going to happen. Okay, so this is the theory. This is the way we think about molecules being formed, bonds being formed. Now, it turns out that we can use catalysis to speed up this process. So catalysis is a way for us to lower an activation barrier. It's a way to create a new pathway to get from starting material A to product B. And catalysts are therefore important because they speed up a chemical reaction, but they're not consumed in the process. Okay, so with these two ideas in mind, let's think about this now. How can we use catalysis to make one enantiomer of a molecule? So don't worry if you're not quite sure. It did take some time for synthetic chemists to figure this out. In fact, the 3 people who first figured it out were awarded the Nobel Prize in 2001. And so the way that we can do this is to use a chiral catalyst. If the catalyst has chirality, it can then create a lower energy pathway to make a molecule that favors one enantiomer of the molecule. Okay, so this is the concept that my group's really interested in, thinking about how do we design new chiral catalysts for a specific synthetic transformation. So this Nobel Prize was awarded to 2 American chemists, Knowles and Barry Sharpless, as well as a Japanese chemist named Naori, for this idea that we could take chiral catalysts and make enantiopure chiral materials. So this is what my group's interested in. This is actually not one of my students. But what we're interested in is this idea of, can we develop catalysts, chiral catalysts, that will allow us to achieve synthetic transformations that are very challenging, to make very complex structures that are biologically relevant. We're also very interested in green chemistry. How do we tackle these challenges in a way that we produce less waste? So with that in mind, I'd like to share with you now very recent results from our research team. And our group is inspired by these beautiful complex structures that are cyclic. So this is a ring, a 14-membered ring containing carbon. You can see that there is a lot of chiral centers on this molecule. All about this ring. So students thinking about constructing this have to think about how do they control the 3-dimensional configuration of every one of these carbon centers. So this is a really big synthetic challenge. We're also interested in these structures, which are sugars attached to this antibiotic erythromycin molecule. This molecule here is important after surgery. It's an immunosuppressant, and it's basically made out of amino acids, forming this large cyclic structure. And one of the challenges, the modern challenges for synthetic chemists is thinking about how do we link these amino acids together and then close this large ring. Okay, so with this idea in mind, I'd like to share with you this first story. So my students have been thinking about, if we want to make this large ring, one traditional approach is to connect a carbon atom to an alcohol in this way. Now, what we've been doing and what our lab is most well known for right now is this idea of actually a new way of building this bond. So breaking a carbon-hydrogen bond and then adding that carbon-hydrogen bond to a carbon-oxygen double bond. And so we've made progress in this synthesis of lactones by developing new chiral rhodium catalysts. So as a result of that, we've been able to make these small lactone structures in enantiopure form. So Bonnie Kim in my lab synthesized this natural product. It's found in celery. It's actually the flavor component of celery. And so when Bonnie synthesized this in the lab, he was able to make it in greater than 99% enantiomeric excess. And he walked around the lab with this flask and asked his lab mates to smell the flask and confirmed that this flask he had smelled exactly like celery, right? Because this is the compound that's responsible for the flavor of celery. It's also been implicated as an anti-stroke agent, as well as having important antioxidant properties. And so this is a relatively simple structure, but we can find in anti-HIV molecules, antibiotic molecules, and much more complex natural type of products that are found in nature. So how did Bonnie do this? It took a lot of perseverance and hard work. He had to screen many variables to improve his enantioselectivity. And so he looks at parameters, for example, the solvent that we mix everything up in, the temperature, the ligand that's bound to the molecule, the counterion that quenches the charge of this catalyst. And so he optimized all of these parameters until he achieved his 97% enantiomeric excess. Whenever my group does that, we do celebrate in the lab because it's challenging to get this high level of selectivity. In addition to this, I mentioned these chiral ligands that are bound to the metal. We like to take these ligands and then input them into a computer and think about what is the three-dimensional structure of this and how is it helping us achieve the enantiomer control. So my students can come up with models for predicting the way that the catalyst is actually exerting its chiral influence. So this is an example of one of the computational models that Peter put together. Okay, so our group's developed a number of these now, what we call hydroacylation reactions with high enantioselectivity. So I'll just point out some of the students that are working on this, Hassan and Peter recently graduated. So Hassan's now a postdoctoral fellow at Yale University, and Peter's just down the road from us at Caltech doing his postdoctoral study. We have a new group of talented students that are working on this project. So Stephen Murphy's continuing, Akin Brook, Dan Kim, and Ching An, as well as Kyle Schinthal are joining this team. And they're working on developing other ways to activate these carbon-hydrogen bonds and develop enantioselective reactions. So I'm really excited about their future contributions to this project. So I'm going to switch gears a little bit now. We've talked about these cyclic structures that have inspired a new way to make lactone structures. Our group's also really interested in these large cyclic peptide structures. So what's the synthetic challenge here? These molecules are relevant to many, many different research fields. So they're nanoimaging agents, they are drugs that are used in the clinic. They're also very challenging structures for synthetic chemists. Now, I discussed this idea of architecture, and it turns out that there's a blueprint for making peptides that's about 100 years old. This blueprint really hasn't changed in the last 100 years. There's been ways to optimize, but the basic strategy for making a peptide has remained the same. The problem with this strategy, however, is that it's incredibly wasteful. So for example, Roche has made Fusion, a peptide-based drug on large scale for treating HIV. But to make 1,000 kilograms of this drug, it requires formation of 45,000 kilograms of waste products. Right? And so this contributes to the cost of HIV-based drugs based on peptide structures. And so what my group's interested in is changing the blueprint for the synthesis of cyclic peptides. And so towards that goal, we came up with a completely different strategy for making peptides, where we build the peptides in a completely different direction. Aside from building up these linear peptides, one of the challenges in closing the ring is that we can imagine that one end of this reactive linear peptide can actually react with another molecule. So instead of ring closure, we can actually start to form polymers or oligomers. And so to conclude, what I'd like to summarize with is this idea that, as a research group, we're interested in new synthetic challenges, but also training the students to think about how to tackle these challenges. And when we think about where new drugs come from, many of them do come from natural sources. They're structures that we can take from nature. But a lot of times, these structures are not optimized for the specific function that we want. And so a student needs to be able to change a specific bond on a molecule and make a derivative of the natural product. Or sometimes, maybe there's no molecule out there that exists to do what we want. And so they actually have to design and come up with completely new structures and make them, in this way, actually about a third of our new drugs are completely synthetic molecules. And so we're training students for the future in terms of jobs as drug designers and constructors of new types of materials and building blocks. Okay, so with that, I'd like to end by thanking, of course, my graduate students for sharing these results. A group of them actually put together some of these slides last night about midnight for me, so I appreciate that. Our alumni as well, and our collaborators. And so I have a group of students that are working in collaboration with other research teams, including the Guam Lab, the NOIC Lab, and the Shea Lab. We're expanding our research efforts into thinking about new materials in chemical biology as well. And I'd like to thank the following agencies for funding. Thank you all for your attention this morning. There actually is no exam, but I'm happy to answer any questions. And I'd like to thank the Dean and Tatiana and Audrey and our sponsors for making this lecture series possible and for the opportunity to be here with you this morning. So thanks very much.